Everyone did actually quite fairly well. I was impressed with the solubility questions. There were a few cases where there were a few misses, but for the most part, everybody seemed to understand solubility. So I'm just going to kind of gloss over the stuff that we didn't directly talk about. Okay? We did end up talking about everything to do with solubility already when we looked at equilibrium the first time, back in chapter, what was that, chapter 14? Pretty sure this is 16. Okay? So we'll just do a little bit of talking on solubility. You can kind of walk me through how you answered your questions. If these were things that you missed, go back through and evaluate and see what happened with them. Okay? So we looked at the unequilibrium unconstant. That was the last thing that we talked about, which was ultimately looking at Q and its relationship with K. And now, in particular, when it comes to solubility. So we've seen this idea before. If Q is less than K, we have too many reactants, so we have to make products. So our equilibrium shifts towards the right. If Q is greater than K, now we have too many products, so the equilibrium shifts towards the left. Okay? Which was the exact process we talked about back in chapter 15 when we're dealing with Q. When we move to chapter 16, come on, we can now evaluate what's happening when we look at solubility. Well, every solubility equation is your solid as a reactant going to the ions as a product. Every single one. So you will always draw out or write out your equilibrium expression in that respect. Which means if we look at our reactants, we're looking at something insoluble, hence it's a solid. If we look at the products, it's dissolved, okay, or aqueous. So if we try to tie this back, ooh, that's an ugly problem that I don't want to go through. If we try to go through and apply this, what we would do is look at our Q value. Okay? If our Q value is less than K, what does that mean? We're going to shift to the products. What are our products? And what was I thinking? In solubility. What are our products in solubility? Aqueous solution. So what happens if Q is less than K? Everything dissolves. Okay, completely soluble. What if Q was greater than K? Shifts towards the reactants. In the case of our reactants, those are all solids. We would expect to see a precipitate or a solid present. Okay? So some of the interpretation comes from actually manipulating numbers, which is what that problem is looking at. And ultimately, that one's even more of an obnoxious one because you have to go through and do all sorts of unit conversions. Okay? Didn't throw any unit conversions at you. We used our standard equilibrium and just what it meant to be K. Okay, what were each of those ideas? Wait a second. No, maybe this is right. Okay. We could then also look at selective precipitation. The textbook goes into this in a lot more detail and something a little bit later. It talks about qualitative analysis and trying to determine what ions are present in an individual solution. Okay? While that material is kind of interesting, and you've done that already in something like 151, it's not something that I could test on easily. Okay, why? You have to know all of the KSPs of all of these different solids. I'd have to provide a glut of information, which would just be a pain to deal with. Okay? But we can look at it in a slightly different perspective, or simplified versions. So if we have a solution that has equal concentrations of lead and barium, so first off, we made it easier because equal concentrations and same charge. Okay? If the concentrations varied or the charges varied, we're looking at all sorts of extra calculations that we would have to run. So now we can just do a comparative analysis. And then it says which salt would precipitate first when you add sodium sulfate. Okay, well, presumably, if we looked up sulfate, in particular lead sulfate and barium sulfate, we would see them both being solids. Okay, so our first pass would be to look those compounds up. Are they both solids, or is one soluble? Because if one's soluble, which one's going to precipitate first? The insoluble one. Okay, so it's a quick, easy analysis. We wouldn't have to do any work. Okay? So before we actually get into this, we would need to know our equilibrium constants, okay? And in particular, our reactions. So we could draw out each individual reaction for each of those potential solids. And we'd look at their KSPs. Okay? Let's say one of these was soluble. Let's pick lead sulfate. So let's ignore the KSP that's given right now. Let's say lead sulfate completely dissolved in water. What could you tell me about the equilibrium constant? I don't want a Q here because it's all K. What would the K expression be? How would you solve for it? Let's write out a K expression. K equals products over the reactants. What are our products?
Lead.
We've got lead ion and sulfate ion. Our reactant is a solid, so it doesn't need to show up in the expression. Okay? If lead sulfate is soluble, what does that mean? It completely dissociates into the ions, which means what's the relative concentrations of your lead and sulfate? Big or small? Big. If those concentrations are big, what happens to the K? It gets big as well. So if we have something that's entirely soluble, our equilibrium expression is huge. Our number is massive. Okay? Let's compare this now. Okay? So if we're looking at something soluble, completely dissolves, we know our other choice, our answer to that, which one precipitates first, would be the other one, because it doesn't dissolve. Make sense? So now what we can go through and do is compare the K expressions. We don't have a massive number. Both of these numbers are relatively small, meaning both of these compounds are relatively insoluble. Which one is, let's go with more soluble. What would we need to look for if it was more soluble? A larger K, just as we went through and looked at already. Which of these has the larger K? What was it? Lead sulfate, which means that one stays dissolved. The first one to precipitate would be the other one, our barium sulfate. Okay? What we're looking at is just K expressions. What does that K value mean? It's the same thing that we've been looking at throughout the entire semester. You need to be able to not just compare numbers, but come up with expressions or ideas behind these. Okay? This was one of the questions, I believe, something along these lines. Okay? The next thing that we could look at, okay, again, we've seen this already. We saw it when we looked at cation effects. Okay? We saw it actually when we looked at acids and bases as far as buffers go. Okay? What happens to solubility in these particular cases? Okay? So if we're looking at the solubility of calcium fluoride, what happens if I add calcium ion to the solution? So if we're at equilibrium and I increase the concentration of calcium, increase the concentration of our products, the reaction is going to shift to the left. How do you know it shifts to the left? We're looking at Le Chatelier's principle. We've put a stress on the system. We've increased the products, which means we need to reduce those back down to equilibrium concentrations. To drop those concentrations, we have to convert them into something. That something happens to be our reactants. Okay? What's the one spin that we would add to this? Instead of saying it goes, what is that, left? Instead of saying our reaction goes leftward if we increase the calcium ion, whoops, sorry. Okay, that's an eraser. If the calcium ion concentration goes up, we could go through and say our reaction goes leftward. Okay, reactants favored. What's the last thing we could add to this? We see a precipitate. If it shifts towards the left, What phase do we have? Solid, which would mean we see a precipitate. All we're adding is one extra word that I can't spell. Solid forms. That's what spell check's for. Okay? So that's an effect on the reaction. What happens if instead we decrease? What happens if our calcium ion concentration, sorry, I'll go to a different color. If we decrease the concentration of calcium, now what happens?
To the right.
It's going to shift to the right. What else could we say? If it shifts to the right, there's one thing. We could say it's rightward. What's the next thing? Products form. What's the next thing? More solid dissolves. Okay? So we're looking at the same ideas that we've already seen. We're now just adding one extra word to it. Okay? And it's a concept you're already aware of. It's either a solid or it's not a solid. Okay? Where this question gets a little bit trickier is what happens if we say change the pH. Okay? When we go through and now we change the pH, everybody flips out. Okay? Well, what happens if the pH changes? So which way do we want to change the pH? Okay, good answer. I agree. Let's change it downwards. What happens when the pH goes down? Okay, we would say it's acidic, which then means the concentration of H plus goes up. Right? How does that affect the equilibrium? If we go back and look at our equation, sorry, that looks like H minus. Do we see H plus show up in that reaction? No. So, oh, no effect. Okay, hold up. What does H plus react with? Anything negatively charged. So let's go to our equation. Do we see anything negatively charged on the reactant or product side? Yeah, we've got F minus. Okay, what happens if we take a look at F minus and we react that with H plus? What do we get? HF. What can you tell me about HF? Careful. It's definitely an acid. It's a weak acid. Because it's a weak acid, what does that mean? We are in equilibrium, which means some of that F minus becomes HF. Do we have F minus or have as much F minus now? No. So what happens? By decreasing the pH, we are removing F minus. So our statement is now if F minus decreases, then what happens? So now we don't have to worry about H plus at all because we went through all of that pH argument to say what happened to F minus, and the F minus decreases. What happens if F minus decreases? We get a rightward reaction. We could say products favored. And we would also say more soluble. Okay? What we're doing is just stringing together a sequence of thoughts or a sequence of comparisons. Okay? It's still stuff that you've done before. You just haven't had it directly told to you. Okay? You do already know how to do all of this. Okay? Questions about that? Is that a question? No? Okay. Other definitions. So this is a legit thing that you didn't know and I wasn't all that keen on talking about, and I'm still not all that keen on talking about, is the complex ion section of your textbook. I did remove that question from Sapling because someone actually told me what it was. Didn't remove it from Connect because don't know what question it was in Connect. Okay. What we're looking at with complex ions, we end up introducing two new kind of definitions, sort of new. A formation and a dissociation. So the formation is where we're forming a complex ion in solution. Okay? It's very similar to the idea of forming a solid, except that new solid happens to dissolve. So we get a very large complex. It's not just a simple ion. It's got a whole bunch of other things attached to it. So it looks really goofy and funny, but it still can be treated the same as a solid. Okay, the same general idea. Okay? We could then look at the dissociation. So instead of making that solid, we can look at taking it apart. Okay? So in the first case, we're starting with technically a complex ion that we then mix with ammonia, and we form a new complex ion. So we now have the formation of our complex ion. If we take a look at the dissociation, now what we're going to do is start with our purple complex ion, dissociate it into its constituent pieces. Really shouldn't have added water onto those. And we get the individual pieces that made it up. Okay? What is the relationship between those two equations? Yes, they are not balanced. Don't worry about that. Okay? What's that? They do have common ions. Not only do they have common ions, they have all the same common ions. If I wrote out a K expression for that first one, whoops, sorry. It was green, right? They're both green. That's not going to be a good choice. Products over reactants. Okay, fancy. That's going to take way too much space, so I'm not going to write it all out. Let's come up with a way to represent that equilibrium constant. Give it a nice symbol. If we just say K, we don't know if we're looking at concentration, if we're looking at solubility, if we're looking at acids or bases. What do we want to add to this? We don't want to say SP. It's not a bad idea, but that says it's a solid. There's no solids in there. This was the equilibrium constant for what? The formation of a complex ion. So let's call it KF. How about the other one? If we look at that equilibrium constant, what's that equilibrium constant for? It's the dissociation of that complex ion, so we can come up with a fancy symbol, KD. What's the relationship between KF and KD? They are the inverse of each other. How do you know they are the inverse of each other? We can go all the way back to chapter 14, where we looked at the relationship between reverse reactions. They're inverses of each other. Okay? The problems when it comes to solving these in the textbook, it comes back to this last statement here. When we go through and solve these, our formation constant for these is usually so large that what we end up doing is saying that when I add nickel ion into an ammonia solution, it completely forms the complex ion. Okay? So if I go through and say it forms it immediately first, then I can look at its dissociation. Okay, which I know sounds a little bit weird, and it's only going to get weirder. What we'll then do to try and determine the concentration of nickel ion present is look at the KD, the dissociation of the complex ion into the individual pieces. Okay? So to solve these, you'll start with your ions. You would immediately drop them into solution and immediately assume they completely convert to the complex ion, then look at how they dissociate. Okay? Why is this important? When you look up equilibrium constants for complex ions, which one do they give you? They give you the formation, not the dissociation. which is a bit odd because all of our calculations involve the dissociation one. Okay? There are a few problems that you could go through and work through in the text. I don't know what question I asked on the connect, and I think the sapling one was just looking at this relationship, the inverse relationship. Okay? Because all it is just a really long, complex equilibrium solve, I don't ask any questions about it. I just want you to be aware of what's going on with it. Okay? Any questions about that? Don't look so depressed. It might make me happy. That was kind of a joke. Kind of. Okay. Qualitative analysis. This goes back to deciding which one precipitates first. We'd have to go through and give you a glut of information again. Okay? So it's an interesting concept to go through. The textbook talks about it. If you ever got interested in water analysis or water purity, something my brother does all the time, this is what they ultimately do. Okay? Do they have any idea of what's going on with equilibrium constants and all that fun stuff? My brother actually does because he took a lot of chemistry and junk like that. But very swiftly you tend to forget it. Why? Because as far as we're concerned, particularly when testing water, if it gives us a positive result that's bad, we don't drink it. Okay? We don't care about the equilibrium constants that go into defining that. Okay? But that's the science behind that technology. You take a sample of water, you add a little bit of sulfate ion. If you see a precipitate, you go, oh, this water's got lead in it, that's bad. Okay? That kind of idea. So it's a neat concept. You can go through and take a look at that qualitative analysis flow chart within the textbook, but it's not something I would ever test on. Just telling you about it. Okay? Questions about any of that? How new was that? Really new? Sort of new. Not new. Okay. So we're on the lower end of that scale. That's pretty good. Okay, so now what we'll go ahead and do, pretty sure, is move into, and I think I've got the numbers right, chapter 17. Would have been nice if I put a title on that. Thermodynamics. Actually,